current. The story is current. Gauss's law for electric fields says that if you have charge, you have electric field. Ampere's law says that if you have moving charges, if you have current, you have magnetic field. So where the heck is the magnetic field coming from? From a permanent magnet. We observe a non-zero magnetic field, and we can, if we follow a path, we're going to get a non-zero answer. So where is the current enclosed by that path? It's a magnet. It's just sitting there. There's no current running in it. That magnet has atoms in it, and those atoms have electrons that to some approximation effectively orbit their nuclei, orbit with particular speed v in a circular orbit of radius r, such that they have an angular momentum L and essentially an associated current. A circular current loop creates a magnetic field. It has a dipole moment, mu. Now, the electron has its own magnetic dipole moment associated with its spin, which is different from its orbital motion. Like how the rotational movement of the Earth is different from its revolution around the sun. It's a little bit of a crappy analogy. Spin in a quantum mechanical sense isn't really a spinning basketball, but it does the job. These orbits are quantized. The component of the atomic angular momentum is an integer multiple of Planck's constant divided by 2 pi. That there is a fundamental unit of atomic magnetic dipole moment associated. We call it the Bohr magneton because we're relying pretty heavily on the Bohr model of the atom. Could be that, could be multiples of that, isn't half of that. That's the minimum value that isn't zero. Quantized. Do this. Magnets, magnetic objects, are arranged in domains, we call them. Domains are clusters of atoms whose magnetic dipole moments align. It's not for certain materials, it is energetically advantageous. Materials like to live in the lowest energy state they can. And for iron and other ferromagnetic materials, an arrangement like this minimizes the total energy. That's where it likes to be. If we expose this sample to an external magnetic field, now all those little atomic dipole moments are going to be, they're going to try to align with the field. So the regions, the domains that already align are going to, they kind of like recruit nearby atoms to align with them, because there's an extra incentive to do that, the presence of the external magnetic field. If we then turn off the magnetic field, the external one, we can achieve like a net bias to one particular alignment more than just sort of randomly oriented domains that sum to zero. The stronger the external field, the stronger the like leftover magnetization we can leave when we're done. This magnetic constant mu is called the permeability of free space, mu zero. A factor K indicates the permeability of a particular material as compared to free space. A paramagnetic material is one that is locally incentivized temporarily to align with an external magnetic field. But then once we remove the effect, it'll go back the way it was. And that's the interaction with the circular magnets and the whiteboard. There's a local attraction because there's a temporary alignment of the magnetic dipole moments. And I just got distracted. I was thinking about two current carrying wires next to each other. If those currents are in the same direction, there is an attraction, which helps explain why no matter which way I flip that coin magnet, it gets stuck to the whiteboard. It's like an induced charge on a nearby conductor when it's brought near a charged object. It's like an induced magnetic field that attracts the coin magnet. The issue there is that it's not always attractive. Some materials, especially organic materials, are diamagnetic, oppositely incentivized by the presence of an external field, and their atoms' magnetic dipole moments tend to anti-align and repel slightly. The result is a magnetic field that is slightly less than it would be if that material were replaced by vacuum. And we can keep track of the up and downness of the relative permeability. Could be greater, could be less than the permeability of free space. We can keep track of that with the magnetic susceptibility. How susceptible is this material to an external magnetic field? As you might expect, ferromagnetic materials have a very high permeability. They like to be magnetized. Iron, uranium, platinum, magnetizable. They are very susceptible. Oxygen gas is not very susceptible compared to that. Carbon is moderately diamagnetic. And this is the last thing I have for you today. In a textbook that I used to have years ago, there was a picture, and like it was one of these like beginning of the chapter, here's a picture, isn't that crazy, let's figure out what's going on, like the way textbooks do, you know. But the textbook claimed that it was a picture of a frog levitating in a magnetic field. But it was like super blurry and out of focus, and like is it floating? I mean, it's a static image. It could just be sitting on like plexiglass or something. I don't know. You know, is this really a thing? I was thinking about that the other day, and I happened to look it up. This is an interesting video because it's at least, I don't know, 90 seconds longer than it ought to be.
Yeah, this is it. Yeah, that was me. Yes, good. Oh, great. This is a nice. Yeah. Actually, don't walk, don't touch anything, please.
It's like a grasshopper or something. But that frog is actually floating, actually levitating in an external magnetic field because the organic material is weakly diamagnetic, and that is enough of a magnetic interaction to oppose the force of gravity. So yeah, apparently that was an actual thing in that textbook that I had years ago. It was an actual frog levitating in a magnetic field. This guy has some neat stuff to say, so I'll unmute him for a second.
With putting a man, to force a man by this magnetic levitation to fly in the air. So technically, we can do it with you without any problems. We put it here. Let's put it here. As you see, it's alive and moving quite happily. No tricks.
There it goes. So a little bit of a, I guess this was a Dutch accent, but the import there is that this magnetic levitation, because our bodily composition is mostly carbon and, you know, maybe some other stuff, but is weakly diamagnetic, and we could also be magnetically levitated in this way with a strong enough field in the right orientation. It's just weird to think about. That's the end of our time, and conveniently, that's the end of my slides. Let me go back to the PowerPoint just for a second. We were talking about para and diamagnetism and ferromagnetism, and that's the end. I just wanted to show you that, yep, that was the end. So I want to say thank you for your attention today. I'm going to stop the recording, and then I'm going to ask if anybody has any questions before we adjourn for the day.